In the previous three lectures, we have studied the basically concepts of fluid mechanics, then viscous potential flow theory, and after that, we have studied the concept of hydrodynamic stabilities. Now we'll apply those concepts on the basically our problems in the plane geometry. In this lecture, we will consider two instabilities. One basically which is known as Rayleigh-Taylor instability, and the second one is Kelvin-Helmholtz instability. We'll consider the geometry as planar geometry. We'll consider them as this one will be x, this will be y, and we'll consider the fluid flow in between, or that there will be two fluids, so the density will be rho 1 mu 1 and this will be rho 2 and mu 2. The width will be different, and also we will consider the finite fluids. In case of the infinite layers, we can take h1 or h2 tends to infinity, so that will be the special cases. Okay, here we will study the effect of heat and mass transfer. The effect of heat and mass transfer at the interface. We know that this heat and mass transfer phenomena is a coupled phenomena. So in this case, basically we will consider the effect of heat along with mass in the analysis. So we'll start with the Rayleigh-Taylor instability. Rayleigh-Taylor instability occurs when we have an statistically unstable situation. Means fluids are at rest, and the upper fluid is more denser than the lower one. Basically, in this case, we will consider like this. We have this basically our fluid arrangement. This channel is like this one. This is x. This is y, and it is rho 2 mu 2. This is rho 1 mu 1. So definitely rho 2 is greater than rho 1, and velocity in both the fluid phases u2 will be 0 and u1 will be 0 in the basic state, or you can say in the equilibrium state. In the equilibrium state, this interface will be basically at y equal to 0, and if we perturb this one, so the perturbation waves will go like this, and this basically height will be represented by eta. So in the perturbed state, y can be written as okay. Rayleigh-Taylor instability occurs when we have a top-heavy arrangement, and for example, just take some oil in a glass, in a glass, and just put some water on it. You will see that the oil will come above the water, and this phenomena is basically known as the our Rayleigh-Taylor instability. Remember one thing, the interface is unstable due to gravity, but we will apply the heat and mass transfer, and we'll see what will be the effect of heat and mass transfer over this statistically unstable interface. So we have taken this problem here. There are two fluids. One has the density rho 2, viscosity mu 2. This one has taken, this is x, this is y. So in the upper fluid, the density is rho 2, viscosity mu 2, and temperature T2, and the width is h2. This is given. And in the lower phase, the density is rho 1, viscosity mu 1, temperature T equal to T1, and the width is h1. We can take h1 as h2, that will be the special case. Here we have taken the most general case, and in the equilibrium state, the interface has temperature T equal to T naught. We are taking the thermal equilibrium system. Okay. Now after perturbation, we will get this interface perturbed. So there will be an elevation in the interface, and then in this time this will be an eta value. So in the initially that was y equal to 0. So after perturbation it will be eta xt. Okay. Now initial velocity is 0. So q1 is 0. Sorry, this is q2 0. and this is Q1 0. After perturbation, this Q2 becomes Q2 dash, and this Q1 becomes Q1 dash. Then we will do the modeling using the viscous potential flow theory. The flow is irrotational. That means the perturbed flow is irrotational. Initially, there will be no flow. So the perturbed flow is irrotational. So in that case, we will take Q1 dash is gradient phi 1 and Q2 dash is gradient phi 2. So in that case, both the fluids are at rest, but the perturbed flow is rotational. And as both the fluids are incompressible, so divergence of Q1 dash is 0 and divergence of Q2 dash is 0. These two implies that del 2 phi 1 is 0 and del 2 phi 2 is 0, means both the potential functions are harmonic. Now, as we stated earlier in the lecture 2, that we cannot enforce the no slip condition in the viscous potential flow theory. So we cannot take the tangential velocity at the rigid boundaries. So what we will do, we'll take that at this rigid boundary there will be no normal velocity across this boundary, and there will be no normal velocity across this boundary. In that case, del phi 2 upon del y will be 0 at y equal to h2, and del phi 1 by del y is equal to 0 at y equal to minus h1. That means that this normal velocity will be 0 at both the boundaries, and so these conditions says the same thing. Now we will take the mass transfer condition at the interface, as we have stated in the lecture 3 how we can derive the mass transfer condition. And then this mass transfer condition states that the mass transfers from one phase is equal to the mass transfers from the other phase. Actually, we are not taking any source or sink at the interface. Therefore, therefore this basically this mass transfer from one phase to the other phase will be same. So this is the mass transfer from phase 1 to 2 is equal to the mass transfer from phase 2 to 1. Now then the interfacial condition for heat transfer. Interfacial condition for heat transfer says that basically the total heat, the total the net heat flux, the total flux basically equal to the total latent heat released during the phase transformation. Actually, we will basically neglect the effect of the kinetic energy, and that net heat flux can be calculated using the basically your heat flux in the second phase minus heat flux in the first phase. So, but at initially, when in the basic state, there will be no heat transfer. So, net heat flux for the first phase is equal to the net heat flux for the second phase. That is given like this. And so, S0 will be 0. Now what we will do, we will consider, we will expand S eta is as in the Taylor series S0 plus eta S dash 0 and so on, as S0 is 0, so A eta is dash 0 and so on. There will be the terms, and we will take S dash 0 as alpha. So for the linear analysis, we will get this condition. And in the case of mass transfer, we can also take the linear condition like this. Remember, this is the basically equation. So how we can basically simplify this one? Rho 1 del f by del t plus gradient phi 1 dot gradient f. So as we know, f is y minus eta. So rho 1, it is minus del eta by del t plus del phi by 1 by del y, sorry, del x ex plus del phi 1 by del y ey dot product with minus del eta by del x ex minus plus ey. And so we will get the condition like this: e rho 1 minus del eta by del t plus del phi 1 by del x into del eta by del x. This should be minus, and plus del phi 1 by del y. In the linear analysis, we have to neglect the terms of order more than 1. So this goes to 0, and we will have the condition rho 1 del phi 1 by del y minus del eta by del t. So for the mass transfer case, we will have rho 1, we will have that rho 1 del phi 1 by del t minus del eta by del t is equal to rho 2 del phi 2 by del y minus del eta by del t. That means for both the cases we have alpha eta, and this one will be alpha eta. Now the interfacial condition for the momentum, we will see the condition, we will calculate that condition using the Bernoulli equation, that the normal stresses will included into the pressure balance equation. So this is P2 minus 2 mu 2 del 2 phi by del y square minus P1 minus 2 mu 1 del 2 phi 1 by del y square is equal to minus sigma divergence of n cap, and then this p can be evaluated using the Bernoulli equation, and we are retaining only the linear terms. This should kept in mind that we are retaining only the linear terms, so we'll get this equation. Now we need to solve the equation, that the part our Laplace equation with the boundary condition. So when del square phi is 0, del square phi is 0 means del 2 phi upon del x square plus del 2 phi upon del y square is equal to 0. We are using normal mode technique, so phi can be written as hy exponential I kx minus I omega t, and so in that case it is minus k square h plus d2h by dy square equal to 0, and so h can be written as c1 cos hyperbolic ky plus c2 sine hyperbolic ky. Similarly, phi 1 and phi 2 will contain c1 and c2, phi 2 will contain c3 and c4. With this cos hyperbolic ky sine and cos and sine. Now what will happen, as we have two conditions that del phi 2 by del y is equal to 0 at y equal to h2, so we'll calculate c3, and at that del phi 2 by del y is del phi 1 by del y is equal to 0 at y equal to minus h1, we can calculate c1. Then we have a condition that rho 1 heat transfer condition is that rho 1 del phi 1 by del y minus del eta by del t is equal to alpha eta, so we calculate c2. And then mass transfer condition similarly says rho 2 del phi 2 by del y minus del eta by del t is alpha eta, so we'll calculate c4. So with the help of those boundary conditions, we can calculate phi 1 and phi 2 in terms of in terms of basically alpha, I omega and c. So in these cases basically we can just calculate our phi 1 and phi 2, and then we will put those values here in this equation. This is basically our uh, dynamical equation at the interface. So after putting those values of phi 1 and phi 2, we will get the dispersion relation d omega, which is a naught omega square plus I a1 omega minus I a2. Here we know that the h1 and h2 both are positive, rho 1 and rho 2 both are positive, so a naught will always be positive. 8a1, then in case alpha is always positive heat transfer coefficient, then mu1 and mu2 are always positive, so in that case a1 is also positive. So in both the cases, and in both the cases the values are positive, but a2 is depending on rho 1 minus rho 2, and as rho 2 is greater than rho 1, So this may be negative or positive depending on these values. Okay, so we will see, we can see that the A2 is basically uh, maybe negative or maybe non-negative. So we need to calculate the conditions under which the interface becomes unstable. Now, what we will do, actually, we are taking the temporal instability. So we are taking the value like this, exponential minus I omega t, which can be written as exponential minus I omega r plus omega I t. And so this can be written as e to power omega I t into e to power minus omega r t. This is the case of all oscillatory instability. That means cos omega rt minus I sine omega rt. But if omega I is positive, and then as t goes to infinity, the amplitude of interface goes to infinity, means system unstable. And if omega I is negative, then as t goes to infinity, e to power omega I t goes to 0, means amplitude of the interface will be will tend to 0, and this case is stable case. Now if omega I is 0, then this is a neutrally stable case, depending whether omega r is non-zero or 0. If omega r is non-zero, then overstability occurs, otherwise it will be a stationary stable situation. So in both the cases, in all the cases, we have to basically our uh, basic concern for related to the omega I. So what we'll do, we'll take omega as omega r plus I omega I. Now I'm taking the real and imaginary parts of this equation. So the real part will be a naught omega r square minus omega I square plus or minus a1 omega I, and minus a2 is 0, and the imaginary part will be 2I a naught omega r omega I, and plus a1 omega r will be 0. From this equation, second equation, we can calculate either omega r is 0 or omega I is minus a1 upon 2a naught. Now, as we already discussed that A naught and A1 both are positive, so this term means omega I is always negative, means system is always stable. But we know that the system is statistically unstable, so we will take the second case, that is omega R0, and so this equation now transfers into A naught omega I square plus A1 omega I plus A2 equal to 0. Now our aim is to calculate the value of omega I when it is positive, because we are looking for the instability. So from here, omega I can be written as minus A1 plus minus under root A1 square minus 4 A naught A2 upon 2 A naught. As A naught is positive, so omega I will be positive only in the case when this value is greater than A1 and we take the positive term, positive sign. So means the instability occurs if A1 square should be less than, or should be A1 square minus 4 A naught A2 should be less than A1 square, means minus 4 A naught A2 should be less than 0, means if A2 is positive, then stability occurs, otherwise system will be unstable. So means A2 greater than 0 will be stable and A2 less than 0 will be unstable. Means the upper region, the A2 equal to 0 is the locus, so the upper region will be stable region and the lower region will be unstable region. Now then for the neutral stability, A2 will be 0, so we have taken this one as 0. Now we have basically solved, we have analyzed the system numerically in the non-linear, in the non-dimensional basically quantities. So we have taken one characteristic value, that h is h1 plus h2, total length of the channel, and this q and the characteristic velocity. If you have any doubt why it is characteristic velocity, you can see the dimension of density is ml minus 3, or just simply we can take g as lt minus 2 and h is l by ml minus 3. So we have l square t minus 2 power half, that is lt minus 1. We have taken this one as characteristic velocity. We have taken other dimensionless variables like this one. This rho cap is the ratio between the density of the basically lower fluid to the density of the upper fluid, and the viscosity ratio is also taken as the density viscosity of the lower fluid and viscosity of the upper fluid. This kappa is the ratio of viscosity ratio to the density ratio. Now, as we are sorry, we have taken those basically dimensionless parameters, so we can get these equations in the dimensionless form. This is the equation in terms of growth rate, and this is the equation in terms of basically neutral stability. Here one thing we can see, that if mu1 and mu2 both are 0, mu1 and mu2 are 0, then this total term goes to 0. Means with taking inviscid fluids, the effect of heat transfer cannot be added into the analysis of Rayleigh-Taylor instability. Means if we want to study the effect of heat and mass transfer, then in the linear analysis, fluids must be viscous. Okay, and then we have calculated the non-dimensional equations. Now we wish to calculate or compute numerical results in terms of various graphs. So what we'll do, we'll take steam in the lower region, and it is steam, or you can say water vapor, and here it is water. So it will be basically top heavy arrangement, and the system is statistically unstable. These values are now given like this. These are the values for water vapor, and these are the values for water, and this is the value for the surface tension at the interface. And now we have plotted the equation equation in the neutral stability form. We have calculated the critical wave number Kc with respect to the kappa, that is the ratio of viscosity to the density. So here we can see that the upper region is stable, as A2 is greater than 0 is stable and A2 less than 0 is unstable. So the upper region is stable and the lower region is unstable. And we see that if there is no heat transfer, there will be no effect of viscosity ratio, because kappa is mu cap upon rho cap. Means without heat transfer, we cannot study the effect of basically viscosity on the neutral stability. But if we taking heat transfer, so in the presence of heat transfer, the stable region increases. We see it is for 1, it is for 5, it is for 10. So the stable region increases, the unstable region decreases. Means heat transfer has stabilizing impact on the statistically unstable interface. Actually, when water in the upper region and vapor in the lower region, so and heat transfer increase at the interface, so in the vapor side there will be more evaporation, and the water side there will be more condensation. Vapor comes in the side of water and will condense. Water goes to the vapor phase and evaporate. In those cases, the perturbation uh, velocity will be very slow, and so the instability delays. And that is the basic thing about the stabilizing impact of heat and mass transfer. Now, vapor fraction is studied in this figure. Here we can see that this is the stable region, and we see that this is for 0.1, 0.01, and this is 0.1. So if the vapor fraction increases, the stable region decreases, means vapor fraction has destabilizing effect. Because if vapor fraction increases, more evaporation will be at the interface, but less condensation, because the water layer is fixed, and therefore more evaporation, that one-sided evaporation, will uh, increase the amplitude of perturbations, and in that case the vapor fraction has destabilizing effect. Now here we have studied the effect of viscosity ratio. Viscosity ratio, we know that mu cap is mu1 by mu2. Mu1 is the viscosity of vapor viscosity, mu2 is the liquid viscosity. So if vapor viscosity increases, flow will be impeded, and then the perturbation growth will be slow. But when the viscosity of the upper fluid increases, definitely it will create more energy in terms of viscous dissipation, and that will basically enhance the amplitude of perturbations. Hence, vapor viscosity has stabilizing effect, and water viscosity has destabilizing effect. Similarly, the effect of density ratio has been shown in this figure. Here also we know that rho cap is rho1 by rho2. So if the density of vapor has an stabilizing effect, and density of the water has a destabilizing effect. And this is true because initially we have taken the statistically unstable situation where rho2 is greater than rho1, and then the system was unstable, and therefore rho2 has destabilizing impact. And these conclusions are written here, that heat transfer for inviscid fluids has no effect on the stability, while it has stabilizing effect for stability of viscous fluids. Vapor fraction has destabilizing effect. Density ratio, viscosity ratio, both has stabilizing effect on the stability of the system. So this is the basic analysis of relative instability when heat and mass transfer was there, and we have used the viscous potential flow theory. Now we are going we are going to study the Kelvin-Helmholtz instability, because in Kelvin-Helmholtz instability, fluids are basically mm, flowing with the different velocities. In this case, what we can do, it is rho2 and mu2, it is rho1 and mu1. Remember, in case of Kelvin-Helmholtz instability, one can take either top heavy arrangement or bottom heavy arrangement, but the fluid's velocity will not be same. Here the velocity is u2 and the velocity is u1. When there is a difference in the velocity at the interface, then pressure perturbations make the interface unstable. In that in the Kelvin-Helmholtz instability, we can take arrangement whether it is statistically unstable or statistically stable, but interface must have a relative velocity, and system will be destabilized. Now here we are taking that the interface is destable, the system is destable, because we have taken basically relative velocity at the interface, and we will study the effect of heat and mass transfer on that interface. In the previous case it was stabilizing, so we will see whether in this case it is stabilizing or not. So what we'll do, we have taken this problem, this is u2, this is u1. So in this case the upper fluid has viscosity has density rho2, viscosity mu2, temperature T2. Same case we have taken, this is x, this is y, but here we should know that q2 initially has u2 I cap in x direction, and q1 has u1 I cap. And if we perturb the interface, in this case q1 dash is equal to u2 I cap plus gradient phi 2, and q1 dash is equal to u1 I cap plus gradient phi 1. And at the interface, T is equal to T naught will be the temperature that will be in the reference state. And again, we are using the viscous potential flow theory, so the perturbed velocity will be the rotational, and we'll solve using the boundary conditions. So again, the velocity potential is given by the some potential function phi, and then fluids are incompressible, so they will satisfy the Laplace equation. Del 2 phi is equal to 0. In that case, again, it is del 2 phi by del y square plus del 2 phi by del x square equal to 0, and we use the normal mode technique, that is hy exponential iky ikx minus I omega t. So also, we cannot enforce the no slip condition at the boundaries. So we'll take the normal velocity at the boundaries are 0. And so del phi j by del y equal to 0 at y equal to minus 1 to power hj, because del phi 1 is minus h1, del phi 2 will be at h2, that we have stated earlier. Similar case we have taken. Now the same thing is that this is the mass transfer condition. We have not taken any basically source or sink at the interface, so the mass transferred from one phase to second one is same as the mass transfers from second phase to the first phase. So this is same, and we will basically linearize this equation, and then this is the energy transfer equation. Now energy transfer equation, we have again taken the simplified formulation given by Shi, because here we have taken the net heat flux will be equal to the latent heat released during the phase transformation. Initially there will be no heat and mass transfer, so initially or basically in the basic state the net heat flux in both the phases will be same. So in that case, that S0 will be 0, and then we will take S eta as dash 0. Now then we calculate this condition, and now after calculating this condition, we can basically write the interfacial condition for the this pressure balance equation at the interface. Similarly, we discussed earlier, it is P2 minus 2 mu 2 del 2 phi 2 by del y square minus P1 minus 2 mu 1 del 2 phi by del y square is equal to minus divergence in cap. So here we can calculate P2 and P1 using the Bernoulli equation, because these pressures are irrotational pressures and we are in the unsteady state, so we can use the potential function. We'll get this equation easily. Now the solution we have discussed earlier, we just take phi as hy, phi as hy, because using normal mode technique, exponential I kx minus I omega t, so we'll get h double dash minus k square h equal to 0. So h will be c1 cos hyperbolic ky plus c2 sin hyperbolic ky. So in case of phi 1 we have c1 and c2, phi 3 divide phi 2 c3 and c4. There will be four constants. Two constant can be calculated using del phi 2 by del y equal to 0 at y equal to h2, so we'll get c3. Now del phi 1 by del y is equal to 0 at y equal to h minus h1, so we'll get c1. These two we can calculate. Now using heat transfer condition we can calculate c2, and then mass transfer using we can calculate c4. Means we can calculate all the constants using four boundary conditions, two at the rigid boundaries and two at the interfaces. Now after getting this eta, phi 1 and phi 2, we will put those values in this pressure balance equation, and so we'll get a dispersion relation in terms of omega is called growth rate, and c, this is again a second order polynomial but containing five constants. It is not exactly same as in the Rayleigh-Taylor instability where we got only three constants. So in this case, a naught is positive, a1 will be negative, then b1 will be positive, a2 will depend on the values, b2 is also depend on the values. So we cannot directly calculate which constant is depend the instability depending on which coefficient. So what we will do, will take omega as omega r plus I omega I. But we know that omega I is positive, then system will be unstable, and omega I is negative, then system will be stable. So we will calculate, or we will basically separate our equation in terms of real part and imaginary part. Then in imaginary part, we calculate value of omega r and then put this value in the real part, and we'll get an equation in terms of omega I. Now this is a fourth order equation, so we'll get 4 roots of omega I. If we wish to plot the maximum growth rate, then we will plot the highest value of omega I. Here all the coefficients are real, so if omega I will be complex, then it will be in pair. Now for the neutral stability, we will take omega I as 0. So we can write the expression a not equal to 0. We can write a not equal to 0, and then by putting the values from the above expressions, the value of a naught, a1, a2, b naught, b1, b2, we will get this expression in terms of this velocity v, where v can be written as u2 minus u1, because we know that the instability occurs due to the relative velocity at the interface. So this basically neutral stability curves are made in terms of velocity. Now we know that the if velocity is greater than the critical velocity, then system will be unstable, and if velocity is less than critical velocity, system will be stable. So we, in this case, we have the lower region is stable and the upper region is unstable. Now here we have plotted the dimensional case. We have not made the system in the non-dimensional form. So we have taken water and water vapor again, but here we have taken the statistically stable situation. That means this time we have taken water in the lower region and steam in the upper region. These values are given, and so we have plotted the velocity in terms of basically wave number, and it is for different vapor fraction. Remember here vapor fraction is above to the water. So as the vapor fraction increases, we see that the vapor fraction increases. This is for 0.1, 0.2, 0.3, 0.4, 0.9. The stable region increases, and so the vapor fraction has stabilizing effect on the interface when the interface is unstable due to the relative velocity. It is because when vapor fraction increases, the water fraction will decrease. In that case, basically more vapor fraction will basically make more inertia force to the interface, and the perturbation growth will be slow. The similar observation from this table can be obtained. See, for point 1 it is 37, then 49, then 40, then 45, then 49, then 50, and we can see that at when the vapor fraction increases at a certain limit, then the increment in the relative velocity is very less. So, but still it is stabilizing. Now, the effect of heat and mass transfer on the stability has also been shown, and we can see that as alpha increases, this is for 0.1, sorry, this is for 1, this is for 1.5, this is for 2. So as alpha increases, the stable region decreases, and that means heat transfer has destabilizing effect on the stability of the system in the Kelvin-Helmholtz instability. It is because when the heat transfer increases, then the vapor and condensation, the vaporization and condensation states basically make the interface more unstable. It increases the relative velocity of the interface. System gets destabilized, and these are the conclusions based on the exactly we did earlier, that the heat transfer in the presence of viscosity has destabilizing effect on the relative velocity, and lower fluid viscosity is low. However, it has stabilizing effect on reactive velocity when the lower fluid viscosity is high. Now we can apply this concept of viscous potential flow theory in the cylindrical geometry as well as in the spherical geometry. Papers are available. If you have any doubt related to your viscous potential flow theory or stability analysis, then we can discuss it somewhere. If you have any question, you can send. Thank you.